As a prologue to the electromagnetic induction lab, I just want to point out the first version of this lab, it worked out beautifully and I did it in my office. And then when we actually did the lab, not through a fault of the students, and I recognize what my mistake was later, sort of, 10,000% error was not uncommon. And so this really struggled with why it was so far off, and I spent hours trying to resolve it. What happened in my office when it worked out so nicely was I think I did circular logic where I used an experimental value to ultimately come up with a theoretical value which matched the experimental value. It was a boneheaded mistake, and after I think 2 years of people doing the 10,000% error, I revamped it. And so when I did this one, I got really excited because I was under 100% error. Relative to the first version of this lab, it works out beautifully. Relative to, let's say, the AC circuit lab, it does not work out as well. I would expect it to be under 100% error. I'll have the same numbers you have in order to do this lab. So we'll just find out what happens. Want you to know that it gets good results only when you compare it to the really horrible results from the previous version. This lab is the electromagnetic induction lab. It says 152 there, but it can be used for 252 as well. So step one, we're talking about two solenoids, and the solenoids we're talking about are right here. We have what is going to be referred to as the large solenoid and what's going to be referred to as the thin solenoid. Just be aware of that. What I'm going to do for measuring the number of coils or distance for the number of coils, I'm just going to take a series of photos which will be sort of spliced after this part of the video for the thin and then for the large. So there's not going to be any commentary. Notice that the metric is on the bottom side here. What we're looking at right there, the number of wires across, that is the number of coils that you would have counted between the two inner pieces of the vernier caliper. The width would be what's measured on the caliper, so the width right there. Length of coils, this is going to be a measurement that I'm going to do now. I'm going to interject that into the video, and then outer hole diameter, inner hole diameter, and then I'll tune back in for the resistance. So the next several measurements will be for the length of coils, L sub sol, D sub hole, and D sub coil for thin and large. I'm going to interject a little bit here. It's going to look like that I didn't measure it properly, but there is an issue of parallax when I'm dealing with a camera. And I have very carefully lined up the inner pieces right here to match up with the end of the coil here and the end of the coil here. I'm just going to zoom in on the measurement of it. And now I'm going to do the same for the large coil. This one should actually be a little bit easier. We'll see if I can get an actually decent picture going. As you'll notice, what I'm doing is I took a picture of basically of what I'm measuring, followed by a zoom in of the actual measurement. And so that's the pattern I'm going to maintain for at least a short while. On that last shot, what I want is I said outer diameter of hole. Recognize there's a ring there. What I really care about is the inner diameter of the coils. And as a quick and dirty, I put down outer diameter of hole. So I'm not actually measuring from inside to inside here, but outside to outside here. And so that's what I was actually measuring. And so it requires a very careful measurements there, and probably doesn't make a huge difference in the long run considering the percent error for this lab. But that, just so you know, that's why I did the measurement I last did. And I'm going to do the same for large. Now I'm measuring the resistance, and so I have it hooked up to the multimeter. It's not a lot of resistance here. And so it is fluctuating at least between 0.0 and 0.1 there for a moment. The actual resistance is going to be somewhere in between those two. It's sort of settled between it. So you can sort of do an estimate by concentrating on how much time it spends on 0 versus how much time it spends on 1. The more time it spends on 0, the closer it is to 0. Don't put down 0 there, but put down an estimate based upon that. So finding the resistance across the large, and this is any fluctuations have a much less significant impact. You can see it was fluctuating right there. It does seem to be fluctuating. However, this one is not a huge impact if you're a little bit off. The other one, unfortunately, yeah, there is. Now we are going to try a different way of actually finding the resistance. While we're here, I just want to point out that this bottom section down here, notice that there's the asterisk down here, means that can be done after you've actually collected all the data. But since you're doing this at home, you can do it slightly differently. This is just unit conversion of the measurements that you have up here. So just be aware that's all that is. Also resistivity of copper. And don't forget to cite the source. Some people are still forgetting to cite sources when I ask them to. All right, so I'm going to set up for the next part. The way we have this set up for the DC, the current's coming out of the red side, that's the high side. It's going to go through into here. This is my multimeter measured on currents in microamps at the moment. And then through here into thin, and then from thin back into the power supply here. This is measuring the voltage of the power supply, and this is measuring the current coming out of the power supply. It's obviously not a lot of current right there. The actual value is not as important as the slope that you're going to get from the graph, and so I'm not worrying about the zeroing or trying to figure out what the base is. It is turned on, but the voltage here is negative 124 millivolts. That's just because it's not zeroed properly. So I'm just going to add just a touch of voltage right there. So now give it a chance to settle some. It seems to be slowing down. We're going to come back to that just in case. And the current, notice the units, it is microamps. And at some point, looks like it backed down, so it's now in sort of the range where it's going to be. And the voltage is in the range. And notice that is millivolts, and that is microamps. So now let's adjust it again. So we're now going to adjust it just a little bit. We now have a different voltage there. And we have a different current. Notice that on the table I have that in milliamps, so you will need to move the decimal point to go from micro to milli. You'll need to move it over 3 places, so that'd be 0.497, at least the way it's, or 6, whatever you decide, for the current. And then our voltage, still roughly what it was, I think, when we left. All right, so now I'm going to adjust the voltage just a little bit more. Ultimately, I need 5 different voltages, so this is the third one. And as that's settling down, let's come over here. Again, it's still displaying microamps, and that's because I actually have the setting on microamps right there. That seems to come close to settling. Back over here for voltage. And I think that's probably close enough to settling right there. And then back over here. All right, so let's adjust another time. All right, that seems to be slowing down. Over here, here's the current. Notice the current is increasing as we increase the voltage, and that's what it should be expected. Also going to do a quick touch of the thin here to make sure it's not too warm, and it's not. All right, it seems to be oscillating back and forth there, and that seems to have settled down. Yeah. All right, so what I'm going to do is I'm going to adjust it. This would be the 5th time. All right, that seems to have slowed down. And then back over here, that is our current. And that seems to have stabilized there. Back over here. And it's now oscillating back and forth. We have a DC power supply here, and then we have the large solenoid. So right now I have it set up so that when I turn it on, current will flow out of this side right here, go through the solenoid and back. We're going to try to check resistance through knowing what the voltage is and the current. And so we have these two multimeters right here, and we're going to get that set up next. So I'm going to pause this and set it up. So we now have this is going to be used for voltmeters, so you can see that that is set on volts. And the two leads, did you measure voltage in parallel? The two leads are in the two ports right there. This is measuring current, and it needs to be measured in series. And so I have current flowing, again, the current is flowing from here through the solenoid, then back into here, and then, so that's into this lead right here, and then from this lead into the meter again. So let's turn it on. And so we have voltage there. I may as well use this as a data point. So that's my voltage, and you can notice that it is in volts. And then over here, we are in 0.37 milliamps. Come on. All right, so there we go. So that is milliamps right there, which it should be because I decided to do it milliamps. That is having issues here. I'm going to check my connections and I'll be back. First data point is, that's our first data point right there, and that is in volts. And over here, this is in milliamperes. They are both set on DC, which it should be. It should be direct current, and DC right there. All right, so I'm going to adjust the knob here, and let's get a second data point. All right, so the voltage is stabilizing, so let's move over here. There is the current. And there is the voltage. So let's, yep. All right. So let's adjust that again. Let's crank it up again. The voltage and the current. Back over to the voltage again. All right, let's crank it up again. New voltage. New current. And back to this in case it's stabilized. Let's go up again. touch. All right, the solenoid is still cool, so we're not getting any, at least if it was warm, then I know we have extra resistance involved, but it's still cool, so we're assuming no extra resistance there. So that should be enough trials. Notice that for the current probe, 600 milliamperes maximum, or 0.6 amperes. And for the differential probe, right there, we have a 6 volt maximum. Now, when we do this test for the large, we have the voltage is the rate limiting step. And when we do it for the thin, then the current is going to be the rate limiting step. We don't want to exceed 600 because then that data becomes questionable. If we do exceed it, hopefully we won't exceed it very often. All I did was remove the other one and put this one in. And so everything else is the same. So we now have the connections right here. So the current is going to be flowing out of the high side through my solenoid and then through my current probe and then back into there. But let's see if we can get a good trial going here. Now there's a slight time delay from when I adjust it to when it actually shows up on the meter here, which is one of the reasons why I think, oh, I'm below 600 milliamps, and then suddenly it shoots it above it, like right there. And notice, as you would expect, that the voltage and the current are in sync with each other. And that should be enough for the data. So now we need to export it. All right, so that should be saved right now. So now we can take the data and post it for you to explore. So we have the basic circuit. We have our power supply here, which is currently turned off. We're doing DC. So the current is going to flow out of the high side into the solenoid, which we're looking at it as a resistor right now, through the resistor and then back. So I want to measure the voltage of the power supply. And so I take my differential voltage probe here and notice that maximum value. And I'm going to connect it up. The convention is that red is the high side, so I just clip that straight into there. And that black is the low side. And so that is going to measure voltage using our LabQuest 2 over here. And then I want to measure current. And so I want to basically intercept the current along as part of the flow here. So I'm going to disconnect at that point. Since the current is flowing out of the power supply through the resistor, the current's going to be coming out here to head back that way. And so I'm going to make a connection here. So I want to connect it here. Current will be flowing through the solenoid into the meter in the direction is indicated. And then from there, back into the power supply. And so let's just double check to make sure everything is right, because I don't want the current probe to be taking the full thrust of the current. It needs to be in series. So current flowing out of there, across through this, and then back. I'm feeling good about that. And then my differential probe is hooked in right there. So this should work. We have sampling rate of 10 samples per second, so we're good there. However, the duration is too short, so let's crank that up to 60. And I think we're good to go. Let's go ahead and zero these. It doesn't make a big difference because what I really care about is the slope. However, just general practice. And let's turn it on. Now, right now there shouldn't be much coming out of it. As you can see, it's still close to zero. So let's go ahead and start that. And now let's just sort of play with the dial. So I'm going to play with the dial and notice that it does adjust there. Turn it up a little bit more. Just getting a whole bunch of data points here. Now 6 volts is my limit on my voltage there, and if you look over here, you'll notice that the value is not quite at 6. So we're getting closer, and now let's just bring it down. And notice the current is also going down as the voltage goes down. And I'm just adjusting the voltage up and down. And this should get us about 600 data points. And there we go. Notice that they are sort of in keeping with each other. So let's turn that off. And again, this was for large. We need to save it, so let me grab my flash drive. Flash drive is in. And so now to save, file. I want to actually export. If I do save, it's going to save it onto the machine. Make sure that it's on the USB there. These are some other things. It's going to save it as a text file. All right, so we now have the power supply hooked to the large right here, and I cranked the voltage adjust all the way up, and that is the voltage when it's at 100%. So you should be able to, I'm hoping that you can see that. That is the voltage, and again, it's oscillating back and forth because that's what we do in physics. So I'm going to stop it here and set up for the next step. So we now have, sort of panning back, looking at the whole thing here. We have current's now going to be running from the high side here. It's going to go through the current probe that's hooked to the LabQuest, and then through large, and then back into here. So that's the setup right there. Because we want a very, very quick glimpse, 10 samples a second is just way too long in between samples. And so we need to up that to 10,000. And so that's going to produce, if you look right there, 180,001 samples. And so we need to really cut that back to 5 seconds. Really don't need 5 seconds, but just want to point out that's where we're setting this. And then click OK. The 5 seconds is just give a little leeway. Hopefully it'll just start, stop. We only need a second, but just in case, we put in 5 seconds there. We now need to know which way is north, because we might have to switch something around here. And so what we're going to use is the magnetic probe right there, which will hook to the LabQuest. And so I'm going to stop this and hook that up. Magnetic field sensor hooked into it. Now the Earth does have its magnetic field, and there's also a matter of zeroing, but the Earth does have its magnetic field. And so that's why you should be expecting to see something there. And a picture of my thumb very briefly. And notice at the end of this, there's that silver dot. It's going to measure the magnetic field that's running perpendicular to that. And so since I want to know the magnetic field coming out of the large solenoid here, I'm going to point it towards that. What's going to happen is if this is the north end right here, the magnetic field is going to be flowing out this way, and it's going to be going towards, basically it's going to be going into this if I'm pointing towards the north end. If the magnetic field is going into the sensor in that direction, it's going to show up as negative. And so that's how we know that the magnetic field is north on this end, by whether we get a negative reading over there. So I am going to turn this on, hold this up next to it, and notice we are getting a positive value. It does increase as we get closer, and it decreases as we get farther away. So I need to flip something around, and probably the simplest thing to flip around will be the leads onto this. And so I'm going to stop this, flip the leads, make sure I've got it set up right, and then we will come back. All right, so I flipped the 2 leads. The current still should be going through in the same direction through the probe, but it now should be going the opposite direction in through the sensor here. And so as I hold this up, notice we now have a negative value, so that means the north end is on the right. Again, it doesn't really matter which side the north end is, other than just standardization. It helps me realize some values later on. And so that's set up. I'm going to stop this and set up for the next part. I do want to comment on being able to sort of guess which way the magnetic field's going to be. In the old coils that the ones that we still have some of them, but in the older ones, it was much easier to see. We didn't have the black tape around here, and it was very obvious which way the wire was coming from here, either going that way or that way. And so we could have actually made a prediction with a right-hand rule. So if the current was flowing that way, if it was flowing around like that, we would wrap our fingers around, and the North Pole would be out that side. If the current was flowing around like this, we could wrap it around like that, and the magnetic field is pointing that way. But it's not easy to tell with these, and so that's one of the reasons it's part of the procedure to sort of take a shot at it, but we don't know for sure. So now we're going to find minimum and maximum current. Because we're doing minimum maximum, we don't have to zero it, but zeroing it always just feels good. And so we have zeroed it, and now I'm going to run it and start with that off. So 10,000, done. Change that to 5 seconds, done. Okay, let's try that again. So I'm going to start that, turn that on, turn that off, stop. And that's the flower pattern that shows up when the LabQuest is it's basically pulling in more data than it can present, and so it just needs time to catch up. You'll also see that in the AC circuit lab. And I'm going to go ahead and stop this and bring back after it's finished with its pattern. I just want to comment a little bit on the sensor while I'm thinking about it. To find the maximum minimum current, we could have used the 10 samples a second. It really wouldn't have taken that long, and it would have been nice and easy. But what we really care about is the rate at which the current is changing, because the rate at which the current changes affects the rate at which the magnetic field is created inside the solenoid. The rate at which the magnetic field changes affects the rate at which the magnetic flux changes. The rate at which the magnetic flux changes affects the induced current in the thin, which we'll measure later. And so that's one of the reasons why we need 10,000 samples a second, is because I really want to know how steep that rise is initially. And it's still going on. I had to redo it because there was a glitch in there, so I'll keep doing it till I get the non-glitch. But again, it's physics, so not only do we rejoice, but we do expect things not to work as perfectly as we hope. So until this thing comes back with results that look nice. That is some nice looking data right there. So what I'm going to do is, first off, let's only look at graph 1. And that steepness right there, there's a slight slope there, and we need to narrow that down. So let's zoom in on that. And let's zoom in again. Oh man, this is just really nice data. That is so much better than what I usually get. All right, so we want to know where the steepest change is. I'm going to highlight the steepest change. It looks like that is the steepest right there. That looks slightly steeper than it does down here. So I'm going to highlight that, maybe slightly less than that. There, that looks a whole lot better. And curve fit, current. And we do have some glare there. Let's see if I can do this without glare. Notice that we do have the brackets there and there so that we know what is going to be fit. And I want to do a linear fit, and there we go. So that is the data that you need to use for number 19. And again, don't forget the units here. That is current in the vertical axis in amperes, and time in the horizontal axis in seconds. And the RMSE, that's the root mean square error. The correlation there, the 0.9993, that is R. When we do graphs using Excel or open off a spreadsheet or Google Docs, the correlation, we can post R squared, which is just this value squared. And so to give you some idea of how the goodness of fit. All right, I'm going to stop it here and set up for the magnetic field bit. After going through all that, I forgot to actually record the minimum and maximum current. And you could pull it off of the table, so it looks like it's about 0 and at about 0.15. And that's all well and good, but I went back the next day and I recreated that aspect, made sure that the voltage was still the same, and recreated it. So the next slide, or next couple slides, are basically what I went back and recaptured in order to get the maximum and minimum current. So look forward to it. All right, so this is the basic setup right here. You're not going to see it when I actually do it because I am missing some extra hands here. So we have the magnetic sensor right there. I did zero it just to try to eliminate the effect from the Earth's magnetic field. And I'll zero it again just before I start. I'm going to start with this 10 centimeters out with the magnetic field 10 centimeters out, then 9, then 8, 7, and then I'm going to go in, and then I'm going to go in by half centimeters as we go in. Now, there is a maximum amount. This thing is set on 6.4 millitesla, so that should be the maximum. We will get readings above that, but it becomes questionable, anything above 6.4, but I'll read it till, either it just pegs out, doesn't change anymore, or we get to the halfway point. I'm basing the distances based upon this table right here. This is table 4. And so I'm going to start at 10 centimeters out. And that's the 10 centimeters out right there. And then go till I'm 5 centimeters in at most. I'm not necessarily going to fill in all of it. And then the theoretical over here, there is a formula that's given. I believe it's written in there which equation to use. Equation 6. So what I'm going to do is I'm going to put it at I'm going to tell you the measurement. Or let's see if I can set this up properly. I'm going to stop this and try to set this up properly, and then we'll run this part of the lab. So not the best setup, but here we go. "10 centimeters out, 9 centimeters out, 8 centimeters out, 7 centimeters, 6 centimeters, 5 centimeters, 4 centimeters, 3 centimeters, 2 centimeters, 1 centimeter, 0 centimeters. So it's right at the entrance, half centimeter in, 1 centimeter in, 1.5 centimeters in, 2 centimeters in, 2.5 centimeters in, 3 centimeters in, 3.5, 4, 4.5 centimeters, 5 centimeters. For the next part, we're going to basically run this trial 5 different times. And the main reason we're going to do it 5 different times is that even though we're doing 10,000 samples a second, we have changes here that are taking place really fast, on the order of microseconds. And so we're trying to capture it. And so we're going to basically do this 5 times, hoping that we get close to an actual good goal here. I'm going to start and stop a couple of times, just because once I start it, it just takes a while for it to catch up, and then we'll do the analysis, and then we'll run the next one. And also the setup over here. So you come back here so you can sort of see the whole mess. We do have the power supply is hooked up to the large right here, and then the current probe is hooked up to the thin. As been talked about before, what's going to happen is we're going to turn the power supply on. That's going to make a current come through here. As the current comes through here, it's going to induce a magnetic field. The magnetic field that's created creates a magnetic flux, and the magnetic flux is going to induce a current in this. Once this reaches a steady current, there's no change in the magnetic field, therefore no change in the magnetic flux, and therefore their current should be 0. So what should happen is when you turn that on, it's when the current ramps up. That was the whole point of that last exercise. When the current ramps up, we will induce a current in this, and then the current is steady, no induced current, and then should go back down to 0. When I turn that off, depends on which one I turn off first, but if I turn the power supply off first, then you should see a spike showing up again as the magnetic field starts to collapse, and then this will induce a current trying to bolster that up. And there it is. So let's go for trial number 1 here. First, we need to turn this on. Then I'm going to turn the power supply on, turn the power supply off, and turn that off. And now we wait. So I'm going to turn this off till it comes back. What we have right there is the spike that happened when the current was induced. And I wanted to get maximum and minimum value, so I don't need to zoom in, but I highlight a certain area there, and I go to statistics, current. So after I had done that recording, I realized that there are times when you turn on the power supply and you get a big spike, and then you get the big current. So for some reason, there's just a glitch in the power supply, so you get a big spike, goes back to 0 in the current, and then you get the current like we saw earlier. Now, when we did the trials earlier and we had that huge spike before we had the normal looking curve, I threw those out. Now, apparently what happened here is that I had a couple of trials where we had that huge spike and the current sensor pegged out.
And so there was a series of trials which were just bad data. So I went back the next day and I recreated that part of the experiment. So the next couple of slides are just pictures of the data that I got from normal operations. And so that's what you're about to see.
I do want to point out over here where it says calculate the experimental induced current by subtracting the smaller from the larger. This is in case it just didn't get zero properly. And so it's just establishing what zero is by doing that. And enjoy. I think that, oh, enjoy. What am I talking about? Don't forget, rejoice, because this is physics.